Done.
You're right.
Hello and welcome back to Calculus 2. So we have last one is alright, savages, just relax. We need to get through the last section in peace.
My mom's gonna ask like who's that yelling? I'm like, I don't know.
It's you, Sharif. That's who it is.
Yeah, how'd you say that on the stream, bro? You are out.
You went to Narc. You went out.
Yo, me and Nick are no longer friends.
Alright.
I see your true characters. You a snitch. You in a mirror tomorrow.
When you get home, the first thing next to her is the. Alright.
So I'll be watching the live stream full blast and everything. Like,
okay, so guys, alternating series. So alternating series will be recognized, right, when you see the -1 to the k or -1 to the k plus 1. So it goes from anywhere to infinity. Now, we can take a look at this term, and all this -1 to the k term does, right, -1 to the k, is creating a sequence of, if you start, let's say, k at 0, you get 1, -1, 1, -1, 1, -1, going on forever. So it alternates between positive and negative numbers. So if you have a sequence which is just a sequence an equals 1 over n, the sequence will just have the dots approaching the number line, going like this forever. But if you have the sequence that is alternating, so now we have bn to be alternating, so instead of 1 you write -1 to the n over n, then you will have this, and then the next number is on the other side but closer to the axis, then the next number is closer still, so they now keep jumping the side, right? So they alternate. Now, as you can see, both of these sequences are convergent sequences. They converge to 0, because if you take the limit as n goes to infinity, you will get 0 for both of these sequences. Series are trickier than sequences, so we have to take a look at the alternating series test, which you actually have to follow the path, like on the. We'll draw a tree, and then you will be working your way through the branches of the tree to get to a conclusion. So alternating series will have possible answers as converge conditionally, converge absolutely, or diverge. So if you take a look at the sheet that I distributed, in the comment section over there, you can see that your AK term or AN term needs to be decreasing, and its limit needs to be equal to 0. Okay. So this is what we are going to write now. So this is like a theorem, like a procedure. So we have summation of -1 to the NAN or k, whatever, to infinity, and then we'll say if AN is decreasing and limit AN equals to 0 as n goes to infinity, right? Then we have number 1. If summation of AN is convergent, we have absolute convergence. Number 2, if summation AN is divergent, we have conditional convergence. And then, obviously, if the limit an doesn't go to 0, you have divergence because divergence test kicks in, right? So that you check out on divergence this way. So this one over here, if limit an different than 0, we have divergence. Now, it's kind of hard to follow this, so I like to draw a diagram that we follow. So we start with looking at the problem because we need to make sure that our problem is alternating series problem. So we see -1, and we go from there. So now the first thing that you do is you check the okay. So over here on this arrow, you check that an is decreasing, and you also check that the limit. I'm drawing this bad. I need bigger arrow. There we go. All right, good. That's better. So over here, you check that the an is decreasing and that the limit of an is equal to 0. So if that's a yes, you go and you do the summation without -1 term. And if it's a no, meaning limit an is different than 0, then you have divergence, right? So, and it's divergence test that pushes that, right? So you start with the problem, and then all you need to do is you check what's happening with an. So you take the limit of an. If it's 0 and if it's decreasing, you go on to the branch to continue with your alternating series. If a equal to 0 is not 0, right? If an is not 0 in the limit, then you have divergence by the divergence test. Now, if the limit is 0, but it's not decreasing, the test is inconclusive. Right? So you have to be careful about that. So now, if both conditions are met, you go and you just check an. So you are literally erasing this part from the problem, and you just check. Now, this is one of the 9 other tests you learn. So I'll just put here with this. So use one of the 9 previous tests. Now, what I have is, again, 2 branches. If it's convergent, it goes to absolute convergence, and if it's divergent, it goes to conditional convergence. So I hope you see that these 3 branches into convergent on one side and divergent on the other. Then the convergence splits into 2 with the absolute convergence. Absolute convergence is any convergence we had so far. So we didn't call it absolute convergence, but when your geometric series converges, it's actually absolutely convergent. When your integral test converges, is absolute convergence. So every single convergence we did so far is actually called absolute convergence. We just didn't call it that way. We just simply call it convergence because we have 2 choices, convergent or divergent. Now, with alternating series, you also have the conditional convergence part. So now we have to distinguish between absolute and conditional convergence. Therefore, it is the first time we're making a big deal out of it. So now, when you are following this, so this is your branching, your tree, and anytime you're solving a problem, you are going to run into one of these branches. So let's go and take a look at a problem. So say you have summation from, let's say, 2 to infinity, -1 to the n, and then you have 1/2 to the n. Actually, you know what? I'm going to write all of this better. You have -1/2 to the n. That's it. Let's say this is a problem. So the way you deal with this is you first use algebra to break off the features, right? The first step would be to break off -1, and then you can break it into -1 and then 1/2 to the n like this. And now you see it's alternating series, right? There we go. So you have a 1 on the n and then 1/2 everything raised to the n. Great. So what do you do first? Well, your an is given as 1/2 raised to the n. So you need to check that its limit is 0, and you need to check that it's decreasing. So limit n goes to infinity of 1/2 to the n, right? You can write it that way. Is clearly 0 because you have 1 divided by infinity. And then question about decreasing. Well, you have 1/2 to the n. Obviously it's decreasing. Just if you write out the terms, if you just write out the terms, you will see. So when n is equal to, we're starting with 2, it's a quarter, then 1/8, then 1/16, then 1/32. And you see that each number that you write, next number is always smaller because it has a bigger denominator. So clearly decreasing. So this is why I say it passes both tests. So passed both means go to convergent branch. Now, when you are on a convergent branch, you are supposed to take a look at your problem and solve the series when you take out -1 to the n term. So now we have to consider summation of 1/2 to the n when it goes from 2 to infinity. Now, what do we know about this? What's the answer? Converge or divergent by what test? Come on, let's go. Thank you. So r is equal to 1/2 that's smaller than 1 converges by geometric. Holy nightmare, people, let's go.
Holy nightmare.
So converges by geometric. So what do I have? Look, both conditions passed, and I have convergence on this one, so it's absolute convergence for the problem. So now we say, as the answer, as our essay over here, since an is decreasing and limit of an equals to 0 and summation of 1/2 to the n is convergent series, and we had it labeled as 2 to infinity of -1/2 to the n is absolutely convergent. So it passed all of the criteria. An is decreasing, an limit is 0, and then it converged on the series. So if it converged on the series, the whole thing is convergent everywhere. So we have absolute convergence. All right, so now this is the part where you are going to hopefully understand the meaning and necessity for conditional convergence. And also, why is it called conditional convergence, right? So let's take a look at alternating harmonic series. Earlier, at the beginning of this lecture, I wrote -1 to the n divided by n. We can start at 1, go to infinity. This is known as alternating harmonic series. It's alternating because the 1 in the denominator is replaced by the alternating -1 to the n. So now what we do is we go on with our program, right? The an is 1 over n. 1 over n in the limit, right, of 1 over n is 0. That's cool. And is it decreasing? Sure, it's decreasing because the sequence is 1 over 1, so that's 1, 1/2, 1/3, 1/4, and so on. So we see it's decreasing. So it passes both conditions, and this is immediately passed on to the convergent branch. Once it is a convergent branch, so let me say pass. So passed, go to convergent branch. And now once you're on a convergent branch, you have to check the summation of the same problem when you take out the -1 to the n. So you take out -1 to the n, you're left with 1 over n from n to infinity. And you know that's divergent by p series, let's say. So you have that. And now you have, it's on a convergent branch, but the series diverged, so we end up with conditional convergence. Here is the diagram. We start here, conditions hold, you are on the convergent branch. When you do the test for the series without -1 to the n, you get divergent, and you end up with conditional convergence. Now I want to discuss the idea of conditional convergence. So now let me first write the answer here. So answer. So answer, we have since an is decreasing and limit of an equals to 0, right? So those are the two conditions that it passed to push us on the convergence branch. Since these two guys hold, and summation of 1 over n diverges, series summation -1 over n, right? -1 to n to the n converges conditionally. So that's what we call conditional convergence, CC. Now let's see what it actually, what is the meaning of this and why is it called that way. So what I have is the series or a summation of 1 over n from 1 to infinity versus summation -1 to the n over n. So the one on the left-hand side is called harmonic series, and we know that one diverges by p series integral test or whatever. The one on the right-hand side is called alternating harmonic series, and it's conditionally convergent. So please understand, guys, and you can actually see it here in a solution of the problem, that your alternating harmonic series is convergent under the condition that it's alternating. Because as soon as you remove that condition, it becomes harmonic series and becomes divergent. So every single conditional convergent series is going to be convergent just because alternating piece is present. As soon as you remove alternating piece, it becomes divergent series. So that's why it's called, and it makes so much sense to be called conditional convergence. Converges under the condition that alternating term is present. As soon as you take it out, it becomes divergent series. Done deal, right? So you see that for absolute convergence, well, for absolute convergence, which is our previous problem, we see that we hopped on the convergence branch. Yay, it converges. And then we also see if we remove the -1 to the n, it still converges, right? So regardless whether the alternating term is in or not, regardless, it converges. So absolute convergence converges absolutely, converges all the time. The next one is it converges only under the condition that alternating term is present, and that's that. So now we can just we can do another example. So we had the example for absolute convergence, we had the example for conditional convergence, and over here I also mentioned that this is conditional convergence because if we remove -1 to the n, it becomes divergent. So conditional convergence converges under the condition that alternating term is present. If you remove it, it diverges. That's that. And now go to homework and take a look at some of the examples that are there for absolute convergence. How about, oh, these are done over here, so we can do the, the chart that I gave you. So the book also has the version of the chart, but it's not as good. So here it is, and this is on page 656. So if you want to look at the alternative version of what I gave you, it's much harder to read because it's not a chart, right? It's not separated as well as the one that I gave you. They call the divergence test, not what I have over there, the nth term. And yeah, that's that. They're missing telescoping series on this. Root ratio, comparison, integral is there. So everything is there except telescoping. So there you go. Here are all of these guys, and you can see that each single one of them has -1 to the k, except number 22. You have the number 22 has a cosine of pi k, which is as good. So I want to, since I worked out the other examples, let me work this out with the cosine. So this is number 22. Summation of cosine pi n, or n pi, whatever, divided by n squared from 1 to infinity. So let's discuss the cosine n pi on the side. Cosine n pi. So cosine graph is a wave like this going forever, and every time you have a pi, you can see that your y value is either +1 or -1. Now we know these are discrete functions, so when if you're starting at 0, we are starting at n equals 1, right? So if you start at n equals to 0, you're starting at n equals to 0, your series is 1, -1, +1, -1, +1, -1, and going on forever. And that would correspond to having -1 to the n. Now, if you're starting at n equals to 1, you will have -1, +1, -1, +1, -1, going on forever. So this one is actually -1 to the n, and this is -1 to the n plus 1, because it's shifted by 1. All right. So now I'm going to remove this because we don't need them here. My eraser doesn't work, so the pen. There we go. So now, what do I have? I actually have that my an is just simply 1 over n squared, because the entire cosine n pi is that negative 1 to the n alternating piece. So I don't have to worry about that. So I'm just going to put this arrow like this, going 2 ways, right, and say that's the same thing. So all I have to do is to consider what happens with n with the 1 over n squared. So limit of n goes to infinity of 1 over n squared is equal to 0. That's great. And is it decreasing? Sure, it's decreasing. You can write this as 1 over 1. So we have 1, and then 1 over 2 squared, which is quarter, 1 over 3, so 1 over 9, 1 over 4, 1 over 16, and it will go on forever. So you see that your denominator is growing rapidly, which means that the number you're getting overall is smaller with every iteration. So both conditions are check and a check. Therefore, we go on a convergence branch and we immediately consider summation 1 to infinity of 1 over n squared, which we know it's convergent by p series. Remember that when you are dealing with this, you can be any of the 9 other tests, right? So p series in this case solves this easily. Earlier was geometric and so on, so it depends on what you get. And now we get the answer. It's absolute convergence, right? So answer, since an is decreasing and limit n goes to infinity of an equals to 0, and summation 1 over n squared, or I can just say an, 1 to infinity is convergent, series summation cosine n pi over n squared absolutely converges. That's the answer. So let's take a look at another one. Actually, I'm going to challenge you guys to solve this next problem, which is very interesting in my opinion. Please, for tomorrow, make sure you have 9.1 and 9.2. We are supposed to actually, if we are to work these things properly, we're supposed to cover 9.1 and 9.3 together, and then 9.2 and 9.4 together, because they cover the same topics and they're prerequisites for each other. In any normal book, you don't get a chapter for power series, you just get 2 lectures, 2 lessons. There are 9.1, 9.3 combined, and then 9.2, 9.4 combined. I'm not sure why this book is breaking off power series into a chapter and gives it 4 sections, where sections 1 and 3 are the same topic and sections 2 and 4 are the same topic. But it is what it is. So I will probably cover 9.1 and 9.3 tomorrow, and then I will cover 9.2 and 9.4 on Thursday, and we will be done. We'll talk about the exam right after. Well, actually, wait. When is the exam? Did you guys decide on the test? Let me just write this. So here's the problem for you.
For everybody, man.
Yo,
Everyone said Tuesday.
You need to
Step down.
Wow. Step down your high.
Step down. All right. Actually, you know what? Let's quickly solve this problem. So take 2 minutes. We still have, guys, about 25 minutes, well, 23 minutes left in this class. 23 minutes left. So work on this, and we'll talk about the exam right after this problem. This is the last problem we're covering for alternating series. So work it out. You have the tree, you have the path you're supposed to take. So go one step at a time.
Yo, every time I eat an edible, I feel like I'm off the
When I open the box.
I'm about to put Molly in the water, yeah? Imagine if I put Molly in the water, bro. You're gonna start sleeping, bro.
Is that completely why?
Yeah.
The dosage is high enough?
You can't speak English.
Starts yelling at us like that.
Yeah.
Writing serving. The letters aren't even the same, it wouldn't even be an L.
Yeah, numbers are good. But you hear this talking about drug use? It's just green, bro. That's what you're
These students.
You're very different after. Yeah.
You guys took the road.
More. No, I am doing one I'm near on the time crunch, you only ride.
Who stays here after? I got you. Who stays here after class? What did you get?
My girlfriend. I can't find a ride away from my mom. I just found a ride.
If he needs a ride, I'm gonna hook a brother up.
It's my boy, yeah. I wish he just told everyone that they were here. No, he lives 5 minutes from here. I live like 30 minutes from here. He drives 30 minutes to come back.
Walnut is not that. Not Walnut. Plainfield is that far.
It's like a 20.
It's not that far.
Nah. But he lives in Bridgewater. So this is inconvenient.
And
He still does it though.
I live 2 minutes down the road.
my girlfriend, so she's like on the way up.
Guys, are you done with the problem?
Back down for
Yeah.
go.
Yes.
What is this? Is it convergent or sorry, absolute or conditional or divergent?
Condition.
Oh boy.
Both.
Condition. Absolute.
It's divergent.
Absolute. All right.
He just guessed the only one that left.
No, I didn't. No, he did the whole thing. Look.
Yeah, I closed the notebook and everything. Dude, I don't need proof. I take your word.
I showed her how to do it.
So we first see that we have our an, that it's n factorial over n to the n.
Yo, I thought you said.
Limit n goes to infinity of n factorial divided by n to the n is equal to 0
Say factorial again.
because factorial.
You just said factorial like 3 times.
So
He did though.
so what you have is the factorial is
Y'all let it, man, bro. We in the basement. Who hearing you? Like, we're in the bunker.
He's gonna get censored on the YouTube.
function n to the n grows much faster than the factorial function. So the limit must be 0 because you have a faster growing denominator. When you have a faster function in denominator, the limit as n goes to infinity is 0. So it passes the first condition. Now, is it decreasing? Well, decreasing, and the answer to that is yes, because the function in denominator again is much faster rising. But you can write out the sequence. When you start at n equals to 1, 1 factorial is 1. So you have 1 over 1, so the first term is 1, right? The second term is n factorial, and now you already have 2 over 4, which is 1/2. And then you're moving to the next term, which is 3. 3 factorial is 6, but then 3 cubed is 27, right? So it's 6 over 27. So then you have 4, that's 24 over 4 to the 4, right? No.
256.
256, yes.
My boy, yo, how do y'all do that?
So you see that the denominator grows at much faster rate than the numerator. Therefore, this is also decreasing. So I have pass on the first, pass on the second, onto the convergent branch we go. So now for convergence, on a convergence branch, I have to take a look at the summation of n factorial divided by n to the n from 1 to infinity. And which test do we use for this?
N equals 1 minus 5.
Ratio test. We use the ratio test because we have factorials, right? So we have our an, that it's n factorial divided by n to the n, and we have an plus 1, which is n plus 1 factorial divided by n plus 1 raised to the n plus 1. So now, limit n goes to infinity of, we peel off n plus 1, and we are left with the n factorial divided by n plus 1 raised to the n plus 1 times, over here we have n to the n divided by n factorial. And now these guys cancel. Boom, boom. And last time we said that one of the ways to solve this is to cancel one of these guys. So limit n goes to infinity. We have n to the n plus 1 times n to the n divided by, we'll go n plus 1 times n plus 1 to the n. So now these guys die over here, and we have the limit absolute value n over n plus 1 to the n, as n goes to infinity. And we know that this was, if you remember, we did this already. We did the long division for this. Yeah, it was less than 1, so convergent. So we have AC. Yes, we have AC because, well, so now we write answer and we're done. So since an is decreasing and limit an equals to 0, and summation of an is convergent, series, this is, what is this problem now? It's 26. So series summation -1 to the n of, great, the computer shuts off. A second, I need to look at it. So n plus 1, and then we have n factorial divided by n to the n absolutely converges. So that's the AC over here. Ta-da! That's alternating series. So just learn the tree, right? The branching, and then, yes.
You can go up like 3 steps.
No.
How did you? Why is n plus 1 times n factorial?
Yeah, where did that come from?
Where'd that come from?
From here. I peeled off n plus 1.
Yeah, n plus 1 times n factorial equals n factorial.
Right?
Sure. Right.
That was there in yesterday's lecture, where I taught about factorials for the first time.
That's bigger, I believe.
There it is. So we did ratio test on vanilla problems, and here it is, factorials, and there is the formula in red, n plus 1 factorials, and you're going to see that a lot. So you better have the grip on it. So n factorial is you peel off the n, that's the last term, right? And I show it over there with the 5 factorial. 5 factorial is 1 times 2 times 3 times 4 times 5 for a total of 120. But you can also write 5 factorial as 4 factorial times 5. Further, you can write 5 factorial as 3 factorial times 4 times 5. You can do that as well. You can peel as many terms as you want.
Smart as faithful, I appreciate you.
So, if you like saying, oh, so n factorial is basically n minus.
It's right there, bro.
You can,
n plus 1 factorial equals
if you have n factorial, you can peel n, and then you're left with n minus 1 factorial.
Yeah, no, that's what I'm trying to get at. Yeah.
He's asking for a y. Do you see any y values there?
No, it's n minus. It's essentially just like the n minus 1.
So that's what I used. As you can see, I have that piece right there.
Got it.
So that's what I used.
Yep.
Good. All right. Well, that's that. Let's talk about the exam.
Monday. We done?